start up in a second. Great, you guys. So today's a big day for Virginia Tech. They're back to playing football in person. Let's hope they do well. Or not. So we'll see how they do. So always exciting. So anyway, I think today we're going to finish up our binomial example. I want to spend some time kind of talking about it, playing around with this code. That code is on Slack for you if you want to download it and play around with it. But I think this is where we're at. So I've done the exact same thing that I did last time where we left off. And I started out with the beta half-half prior. So let's remember what the arguments are right here for my code. This is true P. That's that blue line. Where do I use true P? I use it in simulating the data, and I use it to plot where the truth is so that you can compare it. And last time we looked at a couple different priors. We looked at the uniform to start out with, and now I'm advocating maybe we use this other prior, the beta half-half. That one is proper, so it's integrable, and I can add it all up. What happens in the problem with the other thing is when I plug in 0 or I plug in 1 into the beta 0, prior, those aren't numbers. So I divide by 0 when I do that and it blows up on me. And so sometimes people use that. That had a property we kind of like. Maybe our posterior expectation is the MLE. Now, why you want that, I have no idea. That's obviously just a human thing, where it's like, I like the MLE, I like using the expectation, I want them to match. And so you can kind of wiggle the knobs in your prior and get that to happen. Now, I don't know if that's what we want in itself. If you just wanted the MLE, maybe you get the MLE. So what I would think is, if we like maximums, we'd maximize our posterior distribution. We look at the max a posteriori distribution. Matching a Bayesian mean to the MLE, I don't know, I'm not. And I don't find it all that compelling because nobody does it. But you can discuss it. We looked at the uniform. That one is kind of like, I get it. You're thinking about P and you say, I want to put equal weight across P. And that makes sense to me. And so we haven't invoked any mathematical properties in doing that. It just kind of appeals to us. This prior has all kinds of neat properties, the beta half-half. You'll notice, at least pictorially, it's about flat in the middle. And it's doing something on the endpoints. And last time when we left off, I said, say you were trying to estimate something with very, very small p. And the argument by symmetry will hold for very, very large p. So if I had something that was extremely rare, and I went out there and I collected 100 samples, and I never saw the success, because p is like much, much less than 0.01 or something like that. And so I see nothing. I use that asymptotic wald estimator, p hat. In our case, it would be the frequency. It would be 0. So I think p is 0. That's not a bad answer. It's pretty close to 0. Now, I'll tell you, the one thing I hate doing as a statistician, is saying anything is 0 probability or 1. I stay away from those. So, because if it never happens, why am I studying it? Or if it always happens, why are we studying it? So that's just a ground truth. And so I never want to say that, and I never want my inferences to lead that way, unless it really is a 0. But again, why are we studying it if it never happens and we never saw it? So I want my method to be more flexible around those numbers. And as a statistician, the most important thing for me is characterizing variability. It's not just estimating. It's saying there's a range of answers that are good. An answer can fluctuate like this either because of the method I'm using, the statistic I'm using, or the data itself is variable. And so I want to characterize that. I want to be honest and say I'm unsure of things. Now, I used to think of it exactly the opposite, and I would say I'm characterizing my certainties. And certainly, when I talk to clients of the past, they like that. They want me to be sure. but it's our job to let them know you're not always sure. So there is uncertainty. So when we're talking about things like in the news right now, I guess like the Delta variant, COVID, you know, people are saying this is what we think it is. If you look at their intervals on anything, it's like between 4 people are going to pass and 10 billion. So, and they're not characterizing that for us, the uncertainty and everything. And I don't love that. So we see a lot of things on the news where people give you a percentage or they give you a number. What we really want to know is the uncertainty. So we want to characterize that up front. This prior has some ability to kind of inflate how much mass we're putting on 0 and 1. We want to put some mass right around here to prevent us from saying things like zeros. I'm going to give you an exercise on the upcoming homework. I'll probably post it this weekend. We'll talk about it on Monday, and I'll give you a couple weeks to do it. But sometimes people like to build intervals. And this is what this homework assignment will teach you. You may have done this in another class before. But if you end up building kind of the asymptotic walled intervals or exact intervals from your classical stats class, a confidence interval has the property that when you build the interval, it'll cover the truth some frequency of times. So if I say I have an interval and I say it's 95%, then whatever interval I construct should cover the truth 95% of the time. So if I simulate data out of the process, 95% of my intervals should cover the truth, and periodically I should have an interval that does not cover the truth. And so if you do not ever see your intervals not cover the truth, that's a problem in itself, especially if you're reporting 95%. Danielle?
But for Bayesian credible intervals, you can use the interpretation that we kind of gravitate towards, where you can say we're 95% confident or something, right?
You can say, so we haven't talked about it yet, but Bayesians don't call their intervals confidence intervals. Confidence intervals have the property that you're supposed to cover the truth some frequency of time. So it's a statement about the process. It's not a statement of where you think theta lives, a parameter, in this case, P. Now Danielle said she knows a little bit about Bayes, and Bayesians have a different interpretation. So what the Bayesian is saying, when they construct the posteriors, they're giving you a belief distribution in where you think the parameters live. So the Bayesian, if they built a credible interval, and I'll teach you how to do this later, they would say in their 95% credible interval, they would say, I believe the parameter is in this interval, and my belief is 95%, 0.95 on a probability scale. Now, of course, people will say, well, what does that mean? You know, and if you have the opportunity to repeat the experiment over and over again, you might gravitate towards the frequentist interpretation. Now, if you can't rerun the thing and it only happens once, you just have your one-time belief. But if you're in a paradigm where you get to see it repeated times, you might want to calibrate your Bayesian interval so that it has both interpretations. Sometimes Bayesians will give that to you, and sometimes they will not. So you might want to say, and this would be the best of all worlds. We'll see this with the normal example coming up. You want the best of all worlds probably to say, I believe the parameters in here. I got conditioned on the data. I formulated a probability belief statement on the parameter. And I might want that the interval covers at the nominal rate. So if I say 95%, it covers at 95%. If you could have both of those, I'd argue that's a pretty good thing. If you're in a paradigm where you're repeating everything. If it's something that just happens once, then maybe I don't care about the other one. And all I can do is try to calibrate my belief and say what my belief is based off of. So Bayesian is always conditioning off of something. So the data, maybe some other belief statements. We'll get into subjective Bayes a little bit later. But what I like about Bayes is it says, I believe this. It's in here, and I tell you what my belief is based off of. And that's the best we can ever do, is explain why we believe things. What I usually say to somebody when they say, I don't believe that, I say, what would you include? Like, what am I missing? What's wrong with my model? And that's the conversation that happens. So maybe I update my model. So maybe you could have both. So maybe your credible interval Bayesian credible interval could be a confidence interval. Here's a fact. The shortest intervals that I can construct, 95% intervals, using this prior right here, they're going to beat any of your frequentist procedures. It's going to be optimal coverage. So that's kind of an amazing thing. So the beta half-half prior gives you a nice frequentist interpretation. And you will see this on your homework. So Tiana's probably like, I thought Bayesians and frequentists were at odds with each other. How can this be? That the Bayesian can be the optimal frequentist? Yeah, why not? So I'm not going to say that they're always the optimal frequentist, and I'm not going to say that there's a paradigm for always giving you that. There is not. And if there was, that would be pretty cool. But there's at least a mechanism that maybe I can work with a prior and maybe I can calibrate an interval so that it does have good frequentist properties and good Bayesian properties. So what I'd like us to get away from in statistics is this notion, this false dichotomy that there's frequentists and there's Bayesians and they fight. They don't need to. So that's another human thing. We're adversarial. It's built into our DNA, so we're smart people, we can get away from that. So while I'm not going to prove to you that this prior does have that property in this class, I'll let you simulate it and compare it to some intervals that you're used to playing around with. Larry Brown over at University of Pennsylvania proved this back in the 70s. Beta half-half gives you optimal coverage. He wrote a whole paper on it. It's pretty mathematical. It's pretty cool. And so, anyway, Bayesians do have a lot of flexibility. So what the prior is really doing is it's just making sure that your coverage rates over at the endpoints are good and not p hat times 1 minus p hat divided by n. If p hat was 0, you get 0 out of that. But square root over the top is still 0. So that's a bad answer. So the MLE, in our case, where our answer is 0.5, or sorry, our true p is like less than 1%, and our sample size is small, the MLE doesn't give very good answers. And so the Bayesian, however, can give you reasonable answers under small sample sizes because they have this penalizer. It's the prior. So some people think about things like regularized likelihood or penalized likelihood methods. And Bayesians are kind of penalized likelihood methods. I mean, not kind of, they are. Prior is penalizing. The likelihood is characterizing all the joint uncertainties. So those are both good things. Now there are people that will add like a half-half penalty. I think the most common penalty that people use is because Alan Agresti said it in his categorical book, is that you add 2 successes and 2 failures to everything. That's a little bit too much of a penalty. But he says that's a good idea. You probably could have said 1. You probably could have added a half, because as long as we're making things up, I can count for a half success on each side. And that would be very similar to what's happening here. You wouldn't get the full Bayesian posterior belief statement though out of it. Now I don't care which one you do, just as long as you do it. Penalize. I will say that our methods, like that typical Wald estimator, typical estimator that you learn about for coming up with an interval, it works really well when p is about 0.5. So when stuff is common, MLE works pretty decently. So, but when it's close to the endpoints, it doesn't. And so a lot of asymptotic frequentist methods, which mean as I see more and more data, they start to give you the property that you want. They work really well in the middle, but they don't work well next to the endpoints. I'll probably ask you this on homework, or at least I'll ask you maybe if you wanted to study it. But if you wanted, if you were building a confidence interval using the typical estimator, this is the Wald thing if you guys don't know what it is. So p hat plus or minus square root 1 minus p hat divided by n. And then you cut 1.96 to calibrate it to 95%. If that's not familiar to you, just look up your binomial confidence interval, type in Wald into Google, and it'll give you this. It's straight out of Stat 101. If you did use this sort of interval, and I'm not saying it's necessarily, this is what frequentists think is the best thing to do, it's the easiest thing to do, and we can teach it in Stat 101. If P was within 1% of the boundaries, so either what is less than 0.01 or bigger than 0.99, if I wanted, this is supposed to be a 95% interval, I'm going to plug that number in, 1.96. If I said it's good enough, if I ran my simulation study, and I said it's good enough if it's 94 or 96%, so you're within 1% of the rate that you're reporting. My question is what do you think the sample size would have to be for that to work out? So true P's around 1%, be a little bit smaller. I build my interval. I use 1.96, my critical threshold that relates to a 95% asymptotic interval. So we're using a normal approximation, which is inherently not great unless n is big in this example, when p is small. How big do you think n would have to be to report back a nominal rate of 94% or 96%? I personally wouldn't care. If you're reporting 95, and it's actually 94 or 96, I would be okay with that. That's better than most people. How big would n need to be? 30, right? Let's be safe, 31. It won't even come close. What do you think, Danielle? Just give me a number.
Something big.
Something big. How big? Yeah. What do you think?
10,000.
Yeah, it's like 10,000. So I practiced with this, and I'll ask you to do that on homework. It's like 10,000. So you'd need something really big to overcome it. That's not great. And if p was less than 0.001, n would have to be astronomically large. So what that really tells you is maybe don't use this method and use something else. Okay, so let's simulate our first data point, see how this works. So we ended up seeing a 0, and so our likelihood when I used the flat prior, it was just a straight line. It was 1 minus p was my likelihood function. And now, so there's my likelihood function, it's a straight line, but I'm multiplying by my prior. And so you can think of it as I just multiplied the height of the red dashed line by the height of the black dashed line. I multiplied those all the way through, and then I normalized everything so that it was a probability distribution. And that's what my code does. It actually doesn't plot the continuum because you have no ability to do that. It just breaks this interval into about 100 points. Might be more, might be less, you do what you do. But it bends that thing. So the prior has a lot of impact for the first data point. And there's just one data point right here. The prior is influencing this. Hopefully it's influencing everything in a reasonable way. When I see another data point, another 0, you notice that the posterior and the likelihood still look a bit different. I do it again, I do it again, I do it again, and boom, I finally see my first one, and that's what I really like about this, how much inflection there is. That it said, well, definitely cannot be, you know, a 0. Can't be a 1, because I've seen both of them, it's something in the middle.
So why isn't the posterior on a 0, 1 scale here?
It is. So posterior distribution lives between 0 and 1. The posterior distribution integrates to 1 under the curve.
Okay, I was thinking the height.
Yeah, exactly. So the height of a density function can be much bigger than 1. Think about a normal distribution and just squash the variance down. And that thing will get bigger than 1. So densities can be larger than 1. The area under the curve cannot be less than 1. Common misconception. People are like, how can my density be bigger than 1? It has to do with how much variability there is. Those length times width, really, what we're thinking about. So, yeah, so it is bound, it's explaining things between 0 and 1, and the area under the curve is 1. The curve is always above 0. So, that answers that. I just keep adding more and more data. And what we can kind of notice from this is that the likelihood in the posterior are getting closer and closer together. So the prior impact is wearing off. And so it almost looks like the likelihood function. See a little bit more, and they're getting really close to each other. So I usually ask people to plot this in a couple dimensions. That I want to see their posterior next to their prior, next to their likelihood. If all of a sudden the posterior was stuck on the prior, and it didn't look anything next like the likelihood, I would have a big problem with that. You know, the only time I would think it's okay is when you have one or two data points, but I would probably think you shouldn't be doing statistics. So if that's how little data you have, and your whole inference was guided by the prior. Yes, please.
How are you updating the likelihood? So what is changing that's making the dash red line?
So my likelihood looks like this. So here's one way to do it. P, 1 minus P. This is going to be my number of successes. So out of the number of times I flipped it, that's how many times I saw 1. And then I put n minus x. So n is changing, and x is changing. There's another way you can do this. So because we have independent data, I could just look at this. The product I goes from 1 to n, p of xi, 1 minus p to the 1 minus xi, right here. Where the xi's themselves are just elements that are either 0 or 1. So I have them encoded as indicators. I've taken out the n, choose x in all of this because it's a likelihood function. And so under independence, conditional independence, the joint distribution, which is this one, is proportional to the product of the individual distributions that govern just the individual elements. And if you look at this and you product this through, right here, this ends up just looking like p to the sum of the xi's. I goes from 1 to n. And then 1 minus p to the sum of the 1 minus xi's. Right here is I sum over this. The sum of the xi's is equal to the total number of successes. The xi's are 1s and 0s. If I add them all up, that's the total number of successes. You can see the same thing happens here. If I sum across this, this is going to be, I'm going to sum 1 n times. That'll be n. Subtract off the number of successes. So this whole thing right here is the number of failures. If you've taken an inference class, what you'll think of instantaneously is the total number of successes, the sufficient statistic for inferring P. Now, if you didn't know that and you just knew this sort of expression right here, on the chalkboard you would be at no loss. It's all the same expression. But if you went to your computer and you were always producting things and n was big, don't be surprised if all of a sudden your code doesn't work. So producting things that are either big or small on a computer will run you into trouble real quick. And so being able to reduce this into insufficient statistics would help you with a computational headache down the line. We'll be talking about all those issues as we go through things. I will be provoking you with numerical issues also throughout this class. Sometimes I'll help you with it. But I do like to watch you guys hit little snaps. Did I answer your question?
Yeah.
So that's all that's happening. Just that product is just rolling. Now there's other formulations of all this, sequential updating. If I took my prior as the posterior of the previous step and I updated the likelihood through that, that would be equivalent. I will say that later. So when we need a mathematical break, I'll say something simple, show you something that might be already obvious. Anyway, so that's how we're doing all the updating. We notice that these answers right here look pretty decent too. They don't look too different from the answers that we saw before. And so using that prior, either the uniform or this penalized one, if P is near the middle of the interval, so not way over here or way over here, they'll work about the same. So it's only when I have small sample size and I'm next to the endpoint will you start to see a dramatic difference between those things. So I haven't given you a mathematical calculation you can use to derive this prior. Later on, I'll teach you about certain properties we might want. And I'll show you how to derive this prior. So you will eventually have a mathematical way to derive this. Instead of me just telling you beta half-half, seems pretty good. So let's just remember our argument. It was conjugate. I could steer it in a couple different directions. I have a couple knobs I could turn. It's easy to operate with. And it turns out there's a whole bunch of other good, provable stuff that we can get from using this prior.
So before, did you say that if a conjugate prior exists as
Yeah.
how is that provable for
Yeah, for any distribution, you can kind of imagine, what else would I multiply by? You know, can I get that? So if I all of a sudden can, I probably need to be an algebraist to prove this to you. So let's talk about it and see if we can conjure a proof for it. But maybe it's like the, how would I multiply by something different, get something totally different when the likelihood function is staying the same? So for any problem, the likelihood function is given to you by the sampling distribution. And so, not sure if I can conjure a proof like that, but I bet we could go to somebody that's very theoretical. They could come up with this, but it is true. So, there's all kinds of stuff that I don't know how to prove, but I know it's true, right? So, anyway, I saw a proof for somebody showing that a straight line was connected. And it took like an hour and a half for them to prove that. So it's like, I know that's true. I'm not sure I can prove that by all the axioms of mathematics, but you can build things up from the axioms. But I don't know, how would I be able to come up with something different when one piece is always staying the same? So it's going to have something to do with the form of the likelihood. I think after you go through a couple and you start recognizing them, it might become obvious. Right. Exactly. That word, right? Obvious is the word that you use when you really don't know. Believe. Okay. So that's what's going on here. That's what everything does. Let's look at a couple other examples. Like, let's just play around with this prior and see what the influence can be. So let's maybe look at beta 5,5. So keep in mind I've kept all those numbers the same, alpha and beta, as my hyperparameters. And it's just because of the symmetry of the problem. I probably don't want to weigh one side of the coin more than I weigh the other side. And this does the same thing. It makes the prior expectation 1/2 if I keep those numbers the same. But it certainly changes the variability of the prior. So if I make those big numbers, I'm going to have more influence. So if I ended up picking a beta 5,5, I ended up stacking a lot of mass towards the middle of this distribution. Hit that again. So what we can see from all of this is I've just seen a lot of failures, seen a success. My likelihood function looks like that. I guess I've seen all failures in this. But now my posterior doesn't look very much like my likelihood because I cut a lot of weight on my prior inadvertently. Finally, I saw that success in my likelihood in my posterior are very far apart from each other. So this is being very steered by my prior beliefs. So that's probably too strong. So let me just ask you a quick question with this. How much data would you say my prior is worth in this example? So using a beta 5.5 prior, i.e. p to the 5 minus 1, 1 minus p to the 5 minus 1. How much weight in terms of data is this worth? What do you think? What does that mean? Yeah. So it's like the likelihood is worth how many data points here. So if I think about the likelihood, I try to weigh these things on the same scale, my likelihood is worth 10 data points because I flipped the coin 10 times. My prior is having some impact on the analysis. Can I think about it in terms of how much data is the prior with? I can think about it in terms of the likelihood. I can think about that function. And I can think of its impact on this curve that we're building. What do you think? Okay, let's look at the formula. So let's look at our posterior and see if we can maybe think about it algebraically. So our posterior looks like this. Pi p, given all of my data, is going to be proportional to p to the sum of the xi's. I'll write it out that way. So you can see all of the individual elements plus alpha minus 1. 1 minus p to the n minus sum of the xi. Sum of the xi's. I goes from 1 to n plus beta minus 1. I'll remind you that the minus 1 is just part of the saying it's a beta distribution. We always have to factorize that out. So this equation is kind of nice because I can see the data right next to the hyperparameter. And they're on an additive scale. We like additive scales, we can think about it. We can see the contribution in terms of just adding things in. And so the data is coming in right here. And my prior assumption is coming in right there. So can we answer the question, thinking about it a little bit abstractly, is how much data is this alpha worth? So what do you think? It's worth like 5 successes. So this is acting like 5 successes is this alpha right here. And this is acting like 5 failures. So the prior is acting like 10 data points. So the prior is acting like 10 data points that say I flipped the coin and saw an equal number of heads and tails in that. So my posterior is acting like 20 data points almost. 10 of them are real coin flips, and 10 of them are this prior assumption that says, I think the coin is fair, and I feel like very strongly about it. How strongly? 10 data points worth. 5 successes and 5 failures.
So I need enough number of successes and failures to dominate the
Right. Yeah, you want the data to speak louder in all of this. But yeah, I think so. So it's like if I had 10 actual coin flips and I ended up taking a prior and saying this is acting like 10 additional coin flips, maybe the prior is speaking too loud. So we want that number to be smaller. So the beta half-half is weighing the prior like how many data points? Like 1. Exactly. I think what this says is don't make your prior too concentrated. You want it to be fairly diffused. Don't necessarily want it to be uniform. So let's just do it maybe again. Let's say this is like 50. 50, and I'm going to flip the coin 10 times. So I've concentrated my prior, and it's going to take a lot of data to yank it away from that. So my posterior looks like my prior. It's going to take a long time to yank that posterior away. I kind of budged it a little bit, but 10 coin flips wasn't enough. Now, let me just pull this away for a second. Let's just let this automate itself. Got a pause statement in here. I'll let it go a little bit slowly. That's the secret to my animation. Go a whole bunch of times. So I'm going to flip it 100 times now. We can see that the likelihood is the thing that's changing. The prior never changes. So it has the same influence. And very slowly, we're starting to steer the posterior in the right direction. So I agree this is not a great prior distribution. I'll let this go a little bit faster. I'll add more things in there. My likelihood is bending pretty quickly. My posterior is starting to steer in the direction of my likelihood. Finally starting to pull off of that thing. I can't see the top. So Danielle's question, it's just getting peakier and peakier. I don't want to resize everything, but you know what it's doing at the top. And eventually, the likelihood will take over. So asymptotically, the Bayesian is always in good shape. Then eventually, no matter what my prior is, so long as I'm not multiplying by zeros in certain areas, you'll never pull away from that, then eventually my posterior will be good. So if you like asymptotic statistics, Bayes is good asymptotically. So that's supposed to be a bit of a joke. So asymptotics don't mean that much to me. I want to know how well it works with the data set that you actually have. Not as n goes to infinity. If n goes to infinity, we know the truth. We will always know the truth. So it's a nice thing to think about. But you start to see that the prior starts to wear off eventually. And that's that.